Okay, so we're going to look at the complex number system. So there's a few things that you need to remember. I is always written as I. But I want you to recall that I is the square root of -1, right? That's what I means, but you never write the square root of -1, you write I. And then everything else is in terms of I. So as we look at I squared, isn't that the square root of -1, because it's I, times the square root of -1. I squared is I times I. So what's the square root of -1 times the square root of -1? A radical times itself, bless you, is the number under the radical, so it is -1. So I squared has a value that will be replaced with -1. See, you probably are sad you moved to that chair now, right? Because I'm right in her direct viewing. Then I cubed is I times I squared. Well, if I, my volume up for excitement purposes. So if I is I, and I squared is -1, right? Fancy? We're just going to take I times -1, because I squared has a value of -1. So what's -1 times I? -I. So I cubed is -I. And then I to the 4th is I squared times I squared. So I squared is -1. So what's -1 times -1? +1. So that means that I to the 4th has a value always a +1. And then from there, every other power of I falls into one of these 4 categories. In other words, the pattern repeats. So you need to, and I'm going to use the word you need to know, because you don't necessarily have to memorize this if you know how to derive them. I don't ever memorize them because that's what I think through. It avoids the need for memorization. So for instance, if I were trying to find I to the 39th. So to find I to the 39th, you're going to use the following reasoning. I'm going to find how many groups of 4 i's I have. Because if I can group I to the 39th into groups of 4 i's, I times I times I times I, that's I to the 4th. What's the value of I to the 4th? 1. Right? So if I can find out how many I to the 4ths I've got in there, they're all 1. What's 1 times 1 times 1 times 1 times 1 over and over again? 1. So I want to figure out how many groups of 4 I have. So I'm going to take 39 and divide it by 4, because my pattern goes in 4s, groups of 4. So 4 goes into 39. How many times? At most, 9. 4 times 9 is 36. So that leaves 3. Well, okay, so 4 times 9 is 36. What's left over? Thank you. So your remainder is 3. And that's what I'm concerned with, is I have a remainder of 3. That means I have 3 i's remaining. So that means that I can break I to the 39th down. It's no different than I cubed, because I've got 9 groups of I to the 4ths. 9, 1 times 1 times 1 times 1, 9 times. There's just 1. And then we have these the 3 i's left over. So what is the value for I cubed? -I. So really my answer to this is -I. So I to the 39th has a value of -I. Any power of I is either going to have a value of I, -1, -I, or +1. Those are the only 4 possibilities. Any questions on that? All right, look at example 1. We're just going to simply add or subtract. Pretty basic. So, well, before we do that, let's look at our standard form, though. What's wrong? Okay, what are we confused on? Negative I right here. Remember that we got the negative I because I cubed is I times I squared. So I squared has a value of what? Negative 1. So here's I and here's I squared. We don't ever use negative square root of negative 1. So we're going to call that I. And then I times negative 1. I times negative 1. It's like saying x times negative 1. Isn't that negative x? Because I is kind of like a variable, but it represents an imaginary number. Right? We're letting the square root of negative 1 equal I. It still has the same properties as if it were an x. It acts like a variable, even though it's a number that's not real. Because some mathematician got bored one day and decided to create a whole imaginary set of numbers, which actually is useful in calculus. So they do have a use for it. You'll eventually see its use. But for right now, you got to learn the skills that are associated with it. So let's just add and subtract, which is no different than adding or subtracting like terms. So, you could think of the I in terms of x's. No different. But before we look at that, let's talk about the standard form. Let me get a prettier color. So the standard form right here. A plus BI. Standard form is pretty picky. The A right here, this is your real. That's your real part of what's called a complex number. It's not going to have an I attached to it. And then the BI, because it has an I attached to it, this is your imaginary part of the number. And together, these two together equals a complex number. The real part has to come first. The I, the imaginary part, has to come second. If you reverse them, you're going to get marked wrong because standard form is picky. It is what it is. All right, so we're going to collect like terms. So I'm going to collect the 7 because it's just addition, and the 4, what does that give me? 11. And then plus, I've got the real part, which is negative 3 and positive 5. What does that give me? Positive 2i. So that is the complex form for that sum, 11 plus 2i. Now if the I, the imaginary part, were negative, you would not have plus and minus, you would just have a minus. So then look at the negative, the subtraction. Make sure that you're distributing that negative all the way through the parentheses. So what we really have is 2 minus I, minus 8, minus a 3i. You're just distributing a negative, and now you're collecting like terms like we did before. So our real part is 2 and a negative 8. What does that give me? Negative 6. Whoops, I want to put that in red. So I get negative 6. And then my imaginary part is negative I and a negative 3. What does that combine? So we get negative 4i. And that's it. That is your complex number. You're not going to try to factor it or anything like that. That's it. Don't make it harder than what it is. Where the difficulty comes in is multiplying. Okay, so please don't get addition and subtraction confused with multiplying. Some of you did that on your quiz the first week of school when you're asked to collect like terms. In this example, number 1, a lot of you try to multiply there. So make sure that you're grading your homework and you're not doing that. All right, so then look at example 2. This time we are multiplying. And I'm going to just take the 2. You can FOIL or double distribute. So I'm going to take the 2 and multiply it to the second binomial. So 2 times 5 is 10. 2 times negative I is negative 2i. Then we're going to distribute the 3i. So 3i times 5 is a positive 15i. I like to line up like terms. Makes life easier. And then 3i times a negative I, positive times a negative is a negative. And then 3i times I is 3i squared. you cannot leave a power of I other than 1. So we have to take care of that 3i squared. But we'll do that in a minute. So let's go ahead and collect our terms. So we've got 10. Subtract key to the sign of the larger. We have positive 13i. When you collect like terms, the variable string doesn't change. And then minus 3i squared. We have to deal with this 3i squared. What does 3i squared equal? Negative 1. So I really have a negative 3 times a negative 1 because that's what that I squared is. So all an I squared does is change the sign of the term and you drop off the I squared because a negative 3 times a negative 1 is a positive 3. So we end up with 10 plus 13i, and instead of a minus, that changes to a positive 3, just a positive 3. So now you're going to collect your like terms. So I've got a 10 and a 3, which gives me 13, and then I have my plus 13i, and then that is my product. 13 plus 13i. So moral of the story is you have to take care of I squareds, I cubes, I to the 4th. So I squared is a very popular one. It's the same as negative 1. All it does is change the sign of the term and then you drop the I squared. Are you okay with that? You should be remembering this from 3-4, right? Okay. Then let's look at example 3. I've given you a lot of room for a reason. We're going to raise a complex number to a power. So our complex number here is ugly. It's got a lot of fractions in there. But we'll deal with it. And there's a reason this example 3 follows into example 4. So there's a reason why we're doing this. So we're going to find z squared and z cubed. Oftentimes they like to let the whole complex number equal z or w or something like that. So if I'm going to find z squared, so z squared is equal to, you're not going to square the 1/2 and then square the rad 3 over 2i. You're not going to just square them separately. It really means 1/2 plus the square root of 3 over 2i times itself again, 1/2 plus the square root of 3 over 2i. So we're going to have to FOIL this or double distribute. So I'm going to take the 1/2 and multiply it through. So 1/2 times 1/2 is 1/4. Multiply the 1/2 through. You've got 1 times rad 3 is a positive rad 3. Then the denominator is 2 times 2 is 4, and then tack on the I. Then we're going to distribute the rad 3 2 over 2i. So we're going to multiply this here. So I get rad 3 times 1, so I get a positive radical 3 over 2 times 2 is 4, and then tack on the I. So they are identical. They do not cancel out. They're the same sign. And then I'm going to multiply this here to itself. So rad 3 times rad 3 is just a 3. A radical times itself is the number under the radical. The denominator is 2 times 2 is 4, and then we've got I times I is I squared. So then we're going to collect those. So we've got 1/4. And then how many of these do I have? 2, right? So I have 2. So plus 2 of these radical 3's over 4 i's. I've got 2 of those. We'll deal with the reduction, the simplification of that in a minute. And then plus 3/4 I squared. What are we going to do with the I squared? So the I squared changes that sign right there, doesn't it? I squared is equal to -1. So we end up with 1/4 plus, and then doesn't this 2 here cancel into this 4 twice? They're both outside the radical, so you can reduce them. So plus radical 3 over 2i, and then minus 3 over 4. So this minus sign came from that I squared. So one more step, combine your real parts. So the 1/4, what's 1/4 and negative 3/4? So what's 1 and negative 3? Negative 2 over 4, which is negative 1/2, and then plus radical 3 over 2i. When you have a fractional answer, standard form does not like the I in the numerator. Once the I is separated out of the fraction, so that you have a coefficient and then that I. So that's what z squared is. So this is z squared. Let's not lose sight of what we were finding. Then they want you to find z cubed. Doesn't z cubed equal z squared times z? Would you agree with that? So we've just found z squared. So that's z squared. So my z squared is equal to negative 1/2 plus square root of 3 over 2i. So that's z squared. And then z is 1/2 plus the square root of 3 over 2i. Now, this is important to the next problem that we're going to do after this. I want you to note that these look very similar, don't they? Z squared and z look very much alike. Imagine switching these two around and switching these two around. Wouldn't you have a positive minus something, a positive plus something? Doesn't it look like the difference of two squares factor pattern? Right? That's going to be important because I want you to watch what happens when we multiply the difference of two squares factor patterns. These are going to be called conjugates. Do you remember that from Algebra 3-4 and Algebra 1-2? When you rationalize denominators with radicals, with addition and subtraction, we use conjugates. Same thing is going to happen with the imaginary number. So we are going to go ahead and FOIL this. So let's start off with purple. So I'm going to distribute the negative 1/2. So I get negative 1/4. And then a negative times a positive is a negative. 1 times rad 3 is radical 3. The denominator is 2 times 2 is 4. And then tack on the I. Then, let's use... We'll use that color. Alright, so then we're going to distribute the rad 3 over 2i. So rad 3 times 1, and it's a positive times a positive, is a positive radical 3. 2 times 2 is 4, and tack on the I. Aren't these opposite signs? Won't they cancel each other out? Okay, that's what we want them to do. And then we're going to multiply those together. Rad 3 times rad 3 is a positive 3 over 2 times 2 is 4. I times I is I squared. So when we collect like terms, these are going to cancel. And we get negative 1/4. And then what's going to happen with this I squared right there? It changes the sign, so we get a minus here, right? 3/4. What happened to our I? It disappeared, right? And so then we're going to add the opposite, so plus minus. A negative 3 and a negative 1 is a negative 4 over 4 equals negative 1. So here is our solution. So my point is, when you multiply two conjugates together, you get an integer. In other words, no I, which is what we want. So any questions on that before we flip the page over? Perfect. All right, so let's go to the next page. So let's look at conjugates. So here's what a conjugate looks like. really the difference is right here. The middle changes, and this is your difference of two squares factor pattern, a plus b, a minus b. All you do is change the middle sign. The a and the bi remain identical, you just change the sign in the middle. That's it. And so what this is going to give you, the purpose of multiplying two conjugates together is to get rid of the i's. That's the purpose of your conjugates. So look at example 4 where we're, quote, dividing. You cannot have an I in the denominator because technically that I is the square root of -1, and you're not allowed to have a radical in a denominator. It's not considered rationalized. So we're going to take care of this, and I've got to get that I to go away. The only way to get the I to go away is to multiply it by its conjugate. So what is the conjugate of 2 minus I? 2 plus I. And in order to not change the value of this fraction, I have to multiply both the top and the bottom, the numerator and the denominator, by that conjugate. And so we're just going to distribute the 2 into the parentheses. So 2 times 2 is 4. 2 times I is 2I, all divided by, and then I'm going to use the difference of two squares factor pattern. If this is a minus b, a plus b, it should multiply as a squared minus b squared, shouldn't it? So you can FOIL it if you want to, but at this point in math we should be jumping over that and going, oh, well it's just 2 squared, which is 4, minus I squared, which is I squared. What are you going to do with the I squared? So we still have 4 plus 2I, and we have a 4 and a 4 in the bottom, but the I squared changes that into a plus, so it changes the sign, right? And then when the I squared goes away, what number is left there? I don't see anything. 1. So the negative I squared changed into a positive 1. You okay with that? Notice how the i's are gone, and that's what we want. And so then, continue, we got 4 plus 2I all over 5. You cannot leave your answer as one big fraction. Standard form is picky. You have to split it in its two different fraction forms. So you have to divide each of the terms by that denominator. So we really have 4/5, and because the 2I is positive, we have a plus. Take the I out of the fraction, we have 2/5 with an I hanging off to the side. This is your proper answer. Well, that was fun. Shall we try it again? Like, I don't know what classroom you're in, but that wasn't any fun. All right, so let's try it again. We've got an I in the denominator, can't have that. So to perform that division or to rationalize, we're going to multiply by the conjugate of 2 minus 3I. What is that? Yep, so 2 plus 3I. And you have to multiply it to the numerator as well. And this time the numerator has a binomial in it. So we've got a FOIL. So I'm going to take the 5 and distribute it into the numerator. So I get 5 times 2 is 10. And then 5 times the 3I is a positive 15I. Then we're going to distribute the I into here. So I times 2 is a positive 2I. And I times 3I is a positive 3I squared. Have I lost anybody yet? Are we good? And then the denominator, because I know I created a conjugate, we're going to multiply the denominator as a squared minus b squared. So what is 2 squared? 4 minus what's 3I squared? What's the 3 squared? 9. And then the I squared is I squared. So then we're going to collect like terms in the numerator. So we get a 10. And then 15I and 2I gives you 17I. And then what is the I squared going to do to the sign? So we get a negative 3 all over 4. And again, we have this pesky I squared, which is going to change that sign to a positive, and then we have a 9. So now we have a 10 minus 3 is 7, plus 17I, all over 13. Can I leave my answer that way? You have to split it into its fractional parts, and the real part has to go first. So we get 7 over 13 plus 17/13 I. That was awesome. Do not change them into decimals. That would be very bad. Okay, how about we do the last problem? You're almost there. I'm so tired. All right, this one says solve. It doesn't tell you how to solve. I see a quadratic. I could try to factor. I could try to complete the square. I could use the quadratic formula. It doesn't matter. You choose which is best for you. Can I factor this? Are there any factors of 1, because there's no coefficient here, are there any factors of 1 that add to give you 1? That's 1, and 1 is 2. So no, it's not factorable, it's prime. So then if I were to complete the square, I'd have to move the 1 over here, right? I have a minus 1. And wouldn't I have to divide this middle term by 2 and square it? That gives you what? A fraction. Do we like fractions? Oh, I don't. So I personally would prefer to use the quadratic formula. Just saying. So I'm going to use our quadratic formula, which we've gone over. Remember, the quadratic formula is x is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Did we go over that? Yeah, that's what I thought. Oh yeah, we sang it yesterday, right? All right, so we're going to list out what a, b, and c are. So what is a? And I have one side equal to 0, which you must have, so that's good. So what's a? 1. What's b? 1. What's c? Well, that makes it easy. I'm just going to put 1 in for everything, right? So let's write our template. So our template is a quadratic formula without the a's, b's, or c's. So the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. See, I'm the next American Idol. Mrs. Clue needs me in the choir. Maybe. All right. So then A, B, and C, they're all 1. So I really don't have to pay too much attention to this, do I? So let's start to simplify. So I get a negative 1 plus or minus the square root of 1 squared is 1. Count your negatives. Only have one negative. Negative 4 times 1 is negative 4. Times 1 is negative 4. Here's where our imaginary number comes into play, all over 2. So this gives me negative 1 plus or minus the square root of negative 3, all over 2. Negative 1 plus or minus. Now, remember, this is no different than the square root of 3 times the square root of negative 1. Wouldn't you agree? So how do I write that without the negative underneath? Yeah, we like to write the I, so the square root of negative 1 is I. We like to write the I in front of the radical so it doesn't look like it's under the radical. So we're going to write this as I radical 3, all divided by 2. As far as I'm concerned, well, okay, let's break that apart because your standard form doesn't like that, right? So let's break that apart into its real and standard form. So we have, and you can't reduce anything unless, by the way, the Superman triangle of numbers, which is a negative 1, an I, and a 2. Do they all three have anything in common? You cannot reduce anything. You have to look at all three. If these two had something in common, you cannot reduce them. They all three have to have something in common. So we're going to split the real part out is negative 1/2 plus or minus The imaginary part is radical 3 over 2, and now you're going to stick that I way out to the side to make sure that it doesn't look like it's under the radical. Then this would be your proper imaginary answer. So we have 2 of them, right? This time we have 2 of them.